Welcome to a new edition of the Heat Treat podcast. Today we have a very special guest, a lot of experience on surface treatments. We have Craig Zimmerman with us. How's it going, Craig?
Yeah, very good.
So, Craig, we talked briefly before recording that you have wide and broad experience and some time on the heat treat industry, especially on commercial heat treat. And we're going to talk a lot about surface treatments and special processes. But before that, can you just give us a brief description of your career, the companies you're working for right now, and the path you have followed to your current position?
Okay, sure. I guess I started my career in back in college, I guess. I went to the University of Wisconsin out of high school. I did my bachelor's degree in metallurgical engineering, or they changed the name halfway through to material science and engineering. After I finished my bachelor's, I started looking around for a job, but I ended up staying there and doing my master's degree there as well. The way I got into heat treat is about halfway through my master's degree. My professor told me, "Hey, I don't have funding to pay you research assistant funds anymore," and so I had to go out and find a job while I was still finishing my master's degree, and I ended up working for a company called FPM Heat Treating in Milwaukee, which was about an hour and a half drive from the University of Wisconsin, and they had a second shift lab inspector job that where I would go there at night and I would do quality inspection on heat treated parts at their shop during the evening, and then during the daytime I would work on finishing my master's thesis and preparing for my defense, and I think I still had like a class or two I was doing during the days, and that's what ended up getting me into the heat treat field, which at least as far as like the University of Wisconsin goes, there's a lot of people that ended up going into casting. It was a very strong foundry school and casting school. There weren't a lot of people that went into heat treat out of that college. So but yeah, that was how I got into it. After I finished my master's degree, I decided I probably shouldn't have a master's degree and be a second shift lab inspector at a heat treat shop. So then I ended up putting my resume out there, and I ended up getting hired by another company in Milwaukee called Lindbergh Heat Treating. At the time, they were the largest heat treating or commercial heat treating company in the U.S.
That was in the 90s, right?
Yeah, that was 1995 is when I started with them. So I worked at their plant in New Berlin, Wisconsin for a while. I learned some of the processes they did there. About a year later, they transferred me down to their Chicago plant, and I spent probably the next 15 years working out of that Chicago plant or working in a corporate role for them as well. And then in 2010, I ended up leaving Lindbergh. Lindbergh later got acquired by Bodycoat while I was there. And then I joined Blue Water in 2010. And now I've been at Blue Water for the last 14 years. Working at all of our different plants and serving as a technical director for the company.
So very long career with big guys, right?
Yeah, yeah.
Right. Even FPM, Lindbergh, Bodycoat, Blue Water. So you know a lot of big corporate heat treat America, right?
Yeah.
So
except for the larger heat treaters.
Right. So that's how we call it. So Greg, Craig. So we're gonna talk today about surface treatments, right? So I always like to start the podcast as if we're gonna explain this to the general audience. So we know there are different surface treatment, different types. We're gonna talk about your nickname later, right? But can you first describe what is a surface treatment, the applications, and the different surface treatments, and the most popular that there are on commercial heat treatment?
Okay. So, I mean, there's a lot of different, we call them case hardening treatments or surface treatments that we've performed at different locations where I've worked. So I've, obviously carburizing and carbonitriding are probably the most popular, which is a high temperature surface treatment process where you can case harden the exterior surface of metals while leaving the core soft and ductile. Nitrocarburizing is another very popular process that's more of a low temperature treatment that you don't get as much size change and distortion, and so you can use that treatment on finished parts without affecting the dimensions and still get good wear properties and even corrosion properties out of nitrocarburizing. I've done quite a bit of gas nitriding as well, which is another low temperature process where you're diffusing nitrogen into alloy steels and forming these hard alloy nitrides below the surface that give you a good surface hardness as well and wear resistance. And then my specialty has always been boronizing. I've been involved in that for my entire career since I started working for Lindbergh back in 1995, and that's really been my specialty, and my area of focus is boron diffusion into the surface of metals to make the surface very hard.
And that's how you acquire your nickname, the Boronizing guy, right?
Yeah.
You want to share this this type of story?
Yeah, it just kind of started recently, but we've been calling on a lot of oil and gas companies lately. It's a very popular process out in the oil field because it helps with wear resistance and corrosion resistance and a lot of downhole applications. But yeah, as I go through these offices, I think several times in a row I was somewhere, and the guy I was meeting with would call some other people into a conference room and say, "Hey, you got to come in here. The Boronizing guy's here." And so it's like, hey, all these people just keep calling me the Boronizing guy. So
Right.
why not? Why not?
Why not? Okay, got it. So fantastic. So going back, I mean, of course, when you talk about a surface treatment, maybe the on the top of your head is like carburizing. That's like the big one for commercial heat treaters. I know that nitriding and the application with ammonia have gotten very popular among. But let's start with carburizing. You mentioned something very important that we want to talk about, that it's wear resistance. So I just would like to go very, very basic. If you could describe to us what carburizing is and the application or the wanted result, then we can go to carbonitriding. That what's the difference of applying a little ammonia to the atmosphere? We have done a couple of episodes regarding FNC. We can touch on that, and also nitriding, which are highly ammonia applications for wear resistance. But and of course boronizing. I mean, what's like the difference. So you want to go super brief with what you think. How will you describe to a guy in elementary school each process, and if you could give an example of the application, that would be great. You want to start with carburizing, Craig?
Yeah. So I've even talked to my kids about this, when they who don't know a lot about heat treat, but one of the best examples of carburizing that I can think of is like a padlock shackle that everyone uses, while they're in school or what have you. And so the shackles of those padlocks, those are often carburized. And the reason you carburize it is you want the outside to be extremely hard so that you can't cut through it with a file or a saw very easily. But at the same time, you don't want the entire cross section of that shackle to be so hard, because it's also going to be brittle where you could actually break it with a hammer. So the benefit of carburizing is you make the outside very hard so it can't be cut through, but you want the soft material on the inside that's ductile so it'll bend without breaking if it's hit with an impact or something like that. So that, it's that combination of having a hard wear resistant exterior with a soft ductile tough core below it.
Of course. So just to recap this, you want to have a hard surface and a soft core. That's carburizing. That's the application. But you want to go to carbonitriding. What happens when we add a little ammonia and we don't go that intensive on carbon? So what's the process and the application, if you can share with us?
Sure. So in my mind, we'll get a little more technical here. When you're carburizing, you're diffusing just carbon into the surface, and that higher carbon content at the surface of the steel, it basically turns the steel into a high carbon steel on the outside surface and a low carbon steel on the core. When you quench that material, that high carbon surface will transform to martensite, get extremely hard, and the core will transform into a lower carbon martensite, or maybe not even martensite, maybe bainite or perlite, and it'll stay soft. But one of the things is it works really well on alloy steels that have a lot of hardenability. You can get that martensite to form very easily. You may have the ability to cool it not quite so fast and still form martensite. But on a lot of plain carbon steels like 1018 or 1008 or 1010 or 1117, they don't have any alloying elements in them to speak of. So sometimes the carbon alone just doesn't give that steel enough of a high enough hardenability where if you quench it, you may not get a full transformation of martensite. So there you add nitrogen to the surface of the steel. That nitrogen gives you greater hardenability for that alloy near the surface that's now high carbon and high nitrogen. And by having that higher hardenability, you can still get a full transformation to martensite when you quench it, maybe at a slower rate. Whereas without the nitrogen, maybe you would not get all martensite and would not get the best structure and full hardness in that case. So hopefully that wasn't too technical, but
No,
that's
it
really
was not.
the way to describe it.
And is there an application that comes to your mind, like the example you
A
gave
lot
us
of
on?
yeah, a lot of the stamping companies we deal with that make automotive stampings, they don't like to stamp higher alloy materials. You know, it's tough on their dies. It really wears them out. They have a hard time getting a good stamping out of these higher alloy materials that we love to heat treat. So they intentionally want to use these very low alloy or plain carbon steels that don't have great hardenability. They're really not friendly for us heat treaters to try and heat treat. So then you end up using the carbonitriding where you add the nitrogen to help yourself as a heat treater to get that full transformation that you need at the surface.
That's carburizing and carbonitriding. Then when we take carbon out, then we go fully ammonia as our main gas. Then we get FNC and nitriding, right?
Right.
So let's start with nitriding, right?
Okay.
So that's a lot of ammonia, right?
Yeah. So
So
the benefit, well, and it's much lower temperature too.
much lower temperature, right? That's
So
correct.
that's the big distinction I think with nitriding is that, you know, with carburizing, you're heating parts up to at least 1500 Fahrenheit or you know, I should probably say it in Celsius too, but you're heating up to very high austenitizing temperatures and you're quenching in oil and it causes a lot of distortion and size change to the parts and a lot of the components that we carburize have to be final machined after carburizing to clean it up and make all the dimensions correct. Or sometimes you have to clamp temper or straighten these parts after you quench them because you have all this distortion. You know, the beauty of nitriding is that it's done at a very low temperature without a quench. So you can heat the parts up to this low temperature, like 1,000 degrees Fahrenheit, diffuse your nitrogen into the surface using ammonia and then slow cool it back down to room temperature. And you don't have all that size change, distortion, warpage. And so it's nice. You can't get quite as deep a cases with nitriding as you can with carburizing. Yeah, I used to heat treat some massive gears, you know, that were 10,000 pound gears that were as large as I am, and they'd want 1/4 inch K steps, and you can't do that type of K step with the nitriding process. But for a lot of smaller components, you know, you can get at least a shallow to medium K step with nitriding. The only real drawback with nitriding in my mind is you have to use an alloy steel that has nitride forming alloying elements in it to get a good hardness in that nitrided case. If you don't have anything for the nitrogen to react with and form, like a chromium nitride or an aluminum nitride or a titanium nitride, you know, I think there's 6 different alloying elements that form nitrides. You won't have a hard case. So if you nitride 1018 or 1045 steel, you know, you'll diffuse the nitrogen, but you won't get a good hardness at the surface because there's no alloys there to form these alloy nitrides that you need. So you're really restricted in what kind of materials you can use. It's generally a lot of tool steels, stainless steels. There's an alloy called Nitralloy 135 that was kind of designed for nitriding that's fairly popular, but you can't use a lot of the other grades of steel that people commonly use.
Sure, and maybe you can give us a little feedback on this. But back in the days when you know, carburized used to rule everything, and then nitriding began to become more popular. You know, everybody freaked out that nitriding was going to take over, but and then now it's clearly you know, that each process has its size and its applications,
Yeah.
right? And we need like we just mentioned, parts that have a very soft core, but they're very hard on the surface, and parts that they have a nice wide layer for wear resistance. Can you just explain a little bit where those two processes landed at the very end? When you know that carburizing is taking place, on which applications and which industries, and the ones that nitriding was a home run for the ones that implemented it? I mean, you could
Okay.
share some of that.
Yeah, I mean, you know, gearing has always been carburizing more than nitriding, I believe. Although you do nitride some gears, but gearing, you know, you get a really good high compressive residual stress level with carburizing, and so you get a really good fatigue life. And so So like the gearing industry has typically always used carburizing more so than nitriding. Nitriding is used a lot in like forging dies and stamping dies and things like that need some surface wear resistance but they're parts that you can't really quench, or there's a lot of distortion prone parts that people send you drawings, and if you were to try and carburize this part, you'd never be able to get it back to them in the shape that they need to actually fit and function in the application. And so there's a lot of thin parts or long thin parts that need to be kept straight or kept around, that sometimes if you were to try and carburize it, you'd end up ruining the part, and so you're much better off trying to nitride it. But I would say, like, yeah, definitely the tool and die industry uses more nitriding, I believe, and it's more popular there for forging dies and extrusion dies and die casting dies, especially on those tool steel materials that they make those dies out of.
And then let's go to the the brand new process, the latest process, which is FNC. It's called Ferritic nitrocarburizing, and then we have a mixture of gases. So can you go brief into that process? And you want to go a little bit technical, I don't mind. You want to talk
That's
about
fine.
how the ammonia dissociates and how is it different from nitriding?
Yeah. So the beauty of FNC is that you form an iron nitride layer at the surface of the steel where you don't need a high alloy steel to perform this process. So with ferritic nitrocarburizing, you can treat a plain carbon steel or a low alloy steel that doesn't have these nitride alloying elements, and you can still form an iron nitride layer at the surface. And those layers are actually pretty wear resistant. We actually just recently did an ASTM G65 test on one of these ferritic nitrocarburized parts, and it definitely gives you quite a bit of increase in wear resistance over an untreated piece of steel. So it's file hard. It's difficult to cut through a file with some of these pieces. That's a common test that we do with ferritic nitrocarburizing, is to run a file across the surface and see if the file will cut into the surface or not. And it's actually very good for corrosion resistance. There's a lot of automotive brake rotors that get treated with ferritic nitrocarburizing just because the car manufacturers don't want to have rusty brake rotors, because it's a component you can see on the lot when you're shopping for a brand new car. And in the past, they would make these cast iron brake rotors that they would put on the car, and while they're sitting on the car lot as a brand new car, if it rains or gets wet, these rotors would start to rust, and so that was one of their solutions to not have rusty looking parts on brand new cars on car lots, was to start treating these brake rotors with nitrocarburizing so that they wouldn't rust and would look nice and pretty for when you're shopping for your brand new car.
Yeah, I
So,
mean, brakes has been like one of the most popular applications for FNC. Like you mentioned, when everybody is talking gears, they go carburizing. But when they're talking brakes, you're talking about FNC. Will that be an accurate statement?
yeah, and there's a lot of automotive applications for ferritic nitrocarburizing. I've done engine valves in the past that were treated with salt bath ferritic nitrocarburizing. There's a lot of sliding component, or just, yeah, I guess sliding components. Some of the seating components inside of a car are treated with nitrocarburizing. Some of the visor arms for the sun visor, where they have problems with the spring maybe wearing into that visor arm and causing the visor to not actually stay up where it's supposed to. I've treated rocker arms and many other transmission plates with nitrocarburizing. So there's a lot of pieces in your car that are ferritic nitrocarburized.
And last but not least, and the process that you got your nickname from, boronizing. This is not such as usual process. It's a little bit more complex process, a little more pricey for some heat treaters, but you get different results. So would you mind walking us through boronizing? So for the audience, we're going to get an explanation for boronizing from the boronizing guy. So,
There you go.
all right.
Yeah, so the thing so you're right, there's not many people that do boronizing. It's very few companies are doing it. Most people have never heard of it before. But it's a process where you can get extremely high hardness and very high wear resistance. And we have most of the companies that we've boronized parts for, they've tried things in the past like carburizing or induction hardening, or even nitriding, and their components are still wearing out too quickly, even with the hardness that you get out of carburizing or nitriding. And so then they'll try the next thing that's even more wear resistant, which is boronizing. And a lot of the components, at least from a wear standpoint, it'll last generally 2 to 3 to 4 times longer out in the field than a carburized part would. So the crazy thing about boronizing is the surface hardness that you get. You know, with carburizing, you can get surface hardnesses of about 60, 65 Rockwell C. With nitriding, you're generally in the 50s to 60 Rockwell C range. Same thing with Ferritic nitrocarburizing. With boronizing, our surface hardness is generally off the Rockwell C scale. It's actually typically on average with steel, it's about 1,500 Vickers. We boronize some nickel alloys like Inconel, and we can get hardnesses of up around 2,000 to 2,800 Vickers with boronized Inconel. And so it's just got such a higher hardness than any of the other heat treat processes we do. So I've always told people, out of all the different heat treat processes that I've ever done in my life, boronizing is far and away much harder of a surface than anything else that we could ever produce, and it makes it much more wear resistant than anything else.
And what is such an application that will require such a high wear resistance compared to what you get with carburizing or nitriding?
Yeah, so there's a lot of different industries that can benefit from it. It's I always tell people, if you've got parts that are wearing out too quickly and you're having to buy replacement parts all the time, boronizing is often used to make your part last longer, so you're not having to pay for replacement parts so frequently. So it's a lot of aftermarket type components. So the agricultural industry is one big area. There's a lot of components inside combines that see a ton of wear from abrasive crops and sand and soil being pulled through the machines, and they want to wear these metal components out inside of a combine. There's a lot of things in the oil and gas industry. One of the things, if you look at our website, that Blue Water does, we're one of the only suppliers in the world that can boronize tubing used in oil wells. And one of the things you see in this tubing is generally you've got your pump jack at the surface, and then you've got 2 miles of tubing, and then the pump is 2 miles below ground, and it's connected to the surface with a rod, and this rod passes through 2 miles of tubing, and that rod is going up and down, and you can see the pump jack at the surface kind of going up and down. What it's doing is actually pulling that rod up and down that's driving the pump at the bottom of the well. And one of the problems is that rod at different areas is going to be touching the tubing. And as that rod goes up and down, it's scraping on the tubing wall, and it will eventually wear a hole through the tubing wall. And so we boronize the inside of these tubes to make them last many, many times longer, where you don't end up wearing a hole through your tubing wall. The other really cool thing about boronizing down holes is it's super corrosion resistant as well. They have a lot of corrosion problems. Generally at the bottom of an oil well, it's 250-degree temperatures, so it's hot. You've got salt water down there, so it's highly corrosive. You've also got these corrosive gases like CO2 and H2S down at the bottom of a well, and so things want to corrode very quickly down there. And boronizing has been proven to be 7 or 8 times more corrosion resistant than just a regular untreated piece of steel against that type of environment at the bottom of an oil well. So that's another big area for us is oil and gas type components that are used downhole that just wear out all the time and are constantly being replaced. And it's not very cheap to pull 2 miles of tubing out of an oil well and have to replace it all with brand new tubing. They want those things to last as long as possible without having to be constantly maintained.
So the agriculture and oil and gas and places that is very hard to switch the part is a perfect application of boronizing.
Yeah.
When it's the thing really has to last for long, right?
Yep.
Right.
Well, there's a lot of other industries. I've done pumps and valves where you've got metal on metal wear. I've done things like machine gun barrels where we've boronized the inside of a gun barrel. We've done things that cut concrete, some of the tools that cut through concrete where you've got a really abrasive material there, or pumps that pump concrete or abrasive slurries through them. Die casting dies for aluminum shot, die casting, the aluminum is actually very abrasive when you dump it into a shot sleeve, and it can wash out a shot sleeve. And so yeah, there's a whole variety of it's really just it's a wear solution for any kind of people that see tons of extreme wear on their metal parts.
And we talk about the most popular case treatments or surface treatments. Is there another one that you think we forgot? Well, of course, there's LPC, but I'm going to take that under the carburizing
Yeah.
the wing. There's something else that we actually forgot about, surface or case treatment that might be worth speaking in this space?
There's a lot of other coatings and like spray metal coatings and those types of things, and I always kind of keep
That's
them
not heat
separate
treat.
from the heat. Yeah, right. Like it's not a diffusion process, and it's something that's stuck onto a part.
Yeah,
It's not.
but
It doesn't become
but
part of the part. So yeah, as far as
of
diffusion
course a
treatments
lot
go,
of yeah, like black oxide and all those stuff, but that's a different story. But
yeah.
now, having talked about the case treatments, this is what we call a thermochemical treatment, right?
Hmm.
It's heat treatment, but sometimes it's thermochemical, right? Because we're actually playing with the chemistry of the metal, right? Or we're adding uh, carbon parts, or we're adding nitriding particles to the treatment. So, but what trends are you seeing? I mean, of course, we as a civilization and for the progress, we're always thinking about developing new applications or new parts, or seeing where we can manufacture or things more productive, or to have a longer lasting life. What are the trends that you're seeing in the industry? You as a commercial heat treatment, uh, we mentioned the status quo that all of the gears back in the days were thought to be only carburizing. Of course, now we have some gears that are nitriding. We talked about carbonitriding for stampings. We seen you just explained a great explanation about the boronizing applications. But as trends, do you see that like some specific industries, like let's say construction, big guys like the Komatsu or the Caterpillar are going heavily to carburizing, and you see that, or are you seeing maybe some of the light vehicles are going to nitriding? Very briefly, and I know this is a tough question, but which do you see, which in the industries tend to incline to a process and tend to stick with it? Is that something that you see as a whole?
Yeah, that is a tough question. I'm trying to think of a good answer for that. Um, I mean, I think a lot of the traditional processes are kind of staying in their lanes, and there's not a lot of changes. One of the other new processes I guess we didn't mention is, there's this S-phase carburizing of stainless steel, or S-phase carbonitriding that's being done under a bunch of different names around the world. But it's a low temperature super saturation of carbon into like an austenitic stainless steel, and that's another method that is, I think that's probably the newest technology that's hit the market, is this ability to harden stainless steel at very low temperatures without affecting the corrosion resistance at all. So that's another very interesting process for stainless steels. And it's because the problem with nitriding of stainless steels is that you end up negatively impacting the corrosion resistance when you do a traditional nitriding process on it. But if you do these S-phase carburizing or S-phase carbonitriding type treatments, you do it at a lower temperature where the nitrogen or carbon that you're diffusing into the surface doesn't form chromium carbides or chromium nitrides. So that chromium is still free to act as a passive film, so it protects the parts from any type of corrosion by not forming chrome carbides or chrome nitrides. So that's probably the newest thing, it started out with body coat. They were probably the only company that was doing it under the name of Carburizing. And then there's another company that came into the U.S. called Expedite that offers that process as well. And now there's more and more companies that are starting to jump into that market. And the problem with it is it's being sold under a bunch of different trade names, so it's a little confusing probably to the market and the consumers as to what it really is. But that's probably the newest heat treat technology, I guess, that's kind of come into the market.
Also, I don't know if it's first to call it heat treat, but the HIP, the hot
Oh yeah.
isostatic pressing is like the new trend.
Hmm.
Not a surface treatment. Mm, I don't know if to call it a heat treatment or not, because it's under pressure. But
Yeah.
that's like the two trends that
Yep.
back in the days, nitriding and LPC had, and threaten to take everybody's businesses out, and that didn't happen. I don't know if you
Yeah.
agree with that statement. I mean, that's a very tough statement.
Yeah, so I was involved with LPC for quite a while, and I think it's a really neat process. We got very uniform results with it, and we got very good quality results with it. But it's definitely it has some drawbacks. You know, you can't quench the parts quite as hard as an oil quench can. So you're limited in the depth of hardness you can get, and the depth of case you can get, and the amount of transformation you can get. So it's, you know, at least with the gas quenching, it's always kind of been this carburizing process, but it doesn't quite have as good of a quench to it. So I think it's good for some applications, but maybe not as good for other applications. You can't run it as heavy a parts or as thick a wall sections or as heavy a loads. So it's, you know, it's always at this economic disadvantage as well.
And be wrong. I mean, I do believe that every process has its place. And as you're the boronizing guy, I have talked to the nitriding guy, or the carburizing guy, or the FNC guy, right, or the LPC guy. And I do believe that each process has its application, and each process is designed to fulfill uh, an application itself, about, you know, a very strict niche, and that's the diversity of process that we have. So I believe that this thing is going to keep evolving, and we're going to have just the diverse number of process, but nevertheless we're going to need people that understand how to control each process with the different variables, and actually education. So Greg, it's been amazing to talk about processes as a whole. You know,
one of the really
while.
Yeah, I was going to say, one of the really cool things that we've done is, at least with the boronizing process, is we've taken parts that have been carburized in the past, and the company says, you know, the carburizing is okay, but it doesn't last long enough. We actually combine things together. So we will carburize a part first, and then we will run it through our boronizing process to add the iron boride layer into the surface after carbon's already been diffused into it. And then as a third step, we'll reheat and requench that part to harden the carburized case and harden the core, but you still have the boride layer on the outside. So you can end up getting this multi-layer, multi-case, where you've got a boride layer at the surface to give you extreme wear resistance, but then below it, you've got this carburized case to give you good fatigue life and strength below the boride layer to help support the boride layer. Or after you wear through the boride layer, you've still got this carburized case that can continue to give you better wear life. So we've done things like that. We've done other parts that have been induction hardened in the past that have been wearing out too quickly. We've boronized those parts first, and then they still induction harden them after the boronizing process. So and we've also done it with OS-tempering, where we combine boronizing and OS-tempering together to give them a combination of really high surface wear hardness, but then the properties of the OS-tempering that they really like. So it is kind of a cool thing that we've been able to combine boronizing with traditional heat treats and give you kind of a multi-layered type of heat treatment.
I also work with some companies that, you know, they kind of mix processes for their desired thing, or sometimes you don't even understand what they're doing. Like they carburize, they free quench, and then they reheat, they carburize and they press quench, or sometimes they want to, and but you know, that's a spec. You know, we'll play with it, we'll talk with the customer, but customer is always right. And when it's not, we try to figure a way for him to be right with our understanding. Right. So that's how we do it on commercial heat treat. But Craig, you know, we have talked deeply and some technical about processes, but you know, I do believe that commercial heat treaters, as processes get wider and they get more technical, you need people, you need metallurgical engineers, you need staff, you know, people in the lab, people in the shop, management, you know, sales guys that can understand the process, sell it, execute it, analyze it, see what went wrong with. So that takes a lot of time, and that takes a lot of experience. That clearly you have an amazing background. But I believe that the industry right now is being challenged by the lack of new talent with knowledge, right? At the pace that we needed, because the guys with experience, such as yourself, are retiring way faster than the guys that we're bringing to the heat treat industry. Do you have an opinion on that? And what will be an advice for you to the commercial heat treat community, or the heat treat community that is struggling with this? Because back in the days, the metallurgical engineer of a company lasted 30 years, right? And those guys are retiring, right? And they knew all the magic, they knew all the science, they knew all the charts and spells. And when you give this to a new kid, which might have a bunch of potential, but not a bunch of experience, it's very challenging to keep delivering quality product. And when something goes out of the script, to know where to look for the tricks to solve. What's your opinion on that? And this is question not as a metallurgist, but as a heat treat community individual.
Yeah. So it seems like time travels very quickly in the work world. Like it feels like just yesterday, I was the young guy that was kind of the up and comer in heat treat, and I had all these mentors that were teaching me all the things that they knew, and now all of a sudden I'm meeting them out for dinners, and all these guys that I used to work with at Lindbergh are retired, and I'm still the only one working. So it does seem like it happens fast, because it doesn't feel like that long ago that I was the young guy. But yeah, I was just, it's something that at least at Blue Water, we've actually been talking about recently. Like succession planning has to be a really important thing for us going forward. I was just talking to my boss last month about the fact that, I'm 53 right now, and yeah, I've probably got another 10 years maybe to go, but maybe we should start thinking about bringing someone on to start, working as a protege under me, to start learning all the things that I know, and develop them, so that when I retire 10 years from now, then this guy's got 10 years of experience, and he's ready to step into the role. And I had guys like that, Terry Brown and Ed Jameson from Lindbergh, those were my two mentors that really taught me a ton. And, I owe them a lot for teaching me everything that I learned from them. And so I want to be that person for other people someday too.
That's thinking ahead, 10 years. So just as a follow-up question, from the moment that there's a new engineer coming to the real life, outside the university and textbooks, when you actually give him a job on the shop, or a real responsibility, what's the time frame that you believe it's reasonable for the individual to get some experience and have some real life problem solving under a big organization?
Yeah. So
that can lead to a recall, or can lead to a big quality claim? What do you think is the time frame?
Yeah, so I think back to my early career. So for the first year of my working, I did not feel comfortable even talking to customers. I just didn't feel like I knew what I was doing. Anytime I had like some free time where I didn't have anything going on, I'd go find the ASM Metals handbook and start reading through the heat treat chapters to try and educate myself. Because for me, heat treating was a one semester class when I was in college, and we probably only talked about heat treating of steel for a quarter of that, because there are all these other materials you can heat treat. So I didn't learn a whole lot in college about heat treat. So you kind of have to learn it on the job and on the fly. My second year, after I left Lindbergh in New Berlin, they moved me down to Chicago. Then I had to start answering questions. I was the only metallurgist in the plant there. I didn't have a guy over me that was a metallurgist there. So I started taking phone calls from customers, but a lot of times I would take the question from the customer, and I would say, I don't know the answer to that. Let me call you right back. And I would run out to the shop, and I would ask John Blank, who's this guy that had 30 years of heat treat experience, who was just a furnace operator. He wasn't a metallurgist, but he was a really bright guy, seemed to know all this stuff about heat treat that he'd learned over the years. And so I'd go ask him, hey, what's the answer to this question? And he'd give me the answer, and I'd be, oh, okay, I got it. And then I'd go run back to the office and go call the customer and say, hey, this is what I learned, and here's the answer to your question. And after doing that enough times and interacting with all the people out in the shop, you start to eventually learn everything yourself as you get more hands-on experience. But yeah, like I would say at least 2 or 3 years it takes before you get really comfortable.
I will agree. Yeah, and especially expressing yourself with customers, because there's some stuff that you don't want the engineer to mention to the customer. So I will agree
Yeah,
100% with you. So pretty fair. Greg, it's been great talking to you about heat treat. Uh, you know, great. I mean, you're a technical director from Blue Water Thermal Solutions. So that's a lot of responsibility to pass along the knowledge and the process for such a
yeah.
corporation to keep uh, lasting in the future. So all my best, and thanks for having that openness to teach your knowledge to the next generation. There's not many guys that are actually that open to
Yeah,
just to give away a lot of what has caused them tears and blood and sweat. So I do believe that that's the right approach.
yeah.
Greg, would like to say something else to the audience before we end the podcast. I think this has been very valuable information. We talk very technically, but as well as a power player of the industry, is there something you would like
I,
to state to the new generation of heat treaters?
yeah, I'll just kind of follow. I've been really blessed that I got to work for a company like Lindbergh and Body Code, and also for Blue Water, where I've literally been able to go to probably 100 different captive or commercial heat treat shops that these companies ran, and so I've been able to be exposed to a lot of different processes and a lot of different things that I would have never got if I just worked at a smaller heat treat company that had a single location, or maybe even a captive heat treater. So at least I've been able to really broaden my horizons by working for these two really, really good companies. So I don't know. I'm not sure what to say to the future generation other than, the best thing I've ever done is I'm a guy that I have a reputation for getting really dirty, and out in the shop, like half the time you see me, I'm wearing a black t-shirt because I'm black all the time. I've got boronizing powder on me, or quench oil on me, or God knows what. So I guess the best advice I could give anyone young getting into this industry is, like, get out in the shop, climb on the furnaces, and run experiments and learn things from trying different things. But yeah, like, the best thing to do is be hands-on and get involved in the processes, and don't just sit in the office and try and be an engineer from the office.
So you mentioned that you have other 10 years left, but with all these case depth that you have gotten from boronizing and carbon, you have a bunch of wear resistance, so you're gonna last for the next 20 being heat treat. That was a bad joke for this
Oh,
community, but
I I joke with
Greg.
people. I probably have a lot of boron in me right now.
Yeah, right.
That
So you just have to jump on on the oil tank, right? Just
yep.
to get a little more hardness. But thank you so much, Craig. And for the heat treat community, we're uploading every 2 other weeks podcast with power players such as Craig Zimmerman, right? A lot of experience, a lot of, for the heat treat community, a lot of information from the guys from power players. So we'll see you in the heat treat podcast in a couple of weeks.